Hey guys, welcome back to my channel. Today we're going to be discussing PKA, acidity, and basicity. I will also be posting a blank document of what we're about to go through, so you can go ahead, download that, and take notes as I'm talking along here. Alright, make sure to subscribe below, and let's get started. So first off, we're going to be discussing our acid-base reactions, but we need to know what exactly is an acid versus a base. So when starting out, there's three main definitions that we've used. So the first is the Arrhenius, which states that an acid is a compound that increases H plus concentration, and a base is one that decreases. Next, we have the Bronsted-Lowry definition, where an acid is a proton donor. Remember that a proton is really just an H plus ion, and that a base is defined as a proton acceptor. And finally, the one that is really what we're looking at, especially in organic chemistry, is the Lewis definition, where an acid is a compound that accepts electron pairs, and a base is one which donates electron pairs. Now, all of these seem very different, but honestly, they basically all say the same thing, just that the Lewis definition tends to be a more complete definition, and that, there are a few exceptions to just donating and accepting only H+, but if we use the term of electron pairs, it tends to be a more complete definition. But really, most of the time what we're going to be dealing with is H+. So on a lot of the examples we're going to go through today, we're going to use the acid is going to be defined as a compound connected to an acidic hydrogen. So an acidic hydrogen is one that can be donated to a solution. Alright? So now we have our standard acid-base reaction, and we're going to kind of walk through this one and explain what exactly is going on. So first we're going to define our base in our acid. So you can probably tell that the B stands for the base. You're generally going to see a base in blue. And then you're going to see your acid in red. Now, I'm not going to highlight the A as the acid. Instead, I'm going to actually highlight the H. You may see it either way, but later on you'll see why I've done it this way. So remember that in organic chemistry, when we're drawing out a reaction, we draw from the lone pair to the hydrogen that we're connecting with. And this is true no matter what the reaction is, we always draw away from our lone pair of electrons. So we're going to start here. And remember, this is an acid base, so the base is going to grab the hydrogen. And then to complete, the electrons from the hydrogen are now going to fall back onto our acid. Okay? So now, if we look over here, we have B connected to an H, and now it's plus. What does this plus mean? It means that we suddenly have a deficiency in electrons. Therefore, if we have a deficiency in electrons, we have a higher charge, right? Our charge is going to be more positive because the more electrons we have, the more negative it is. But in this case, it's electron deficient because now the lone pair that B originally had is now being shared with a hydrogen, right? So really the B has one less electron than it did before. And so therefore it's going to have a more overall positive charge. The acid, on the other hand, has now gained an electron, right? Because over here we see that when we grab the hydrogen, remember that the electrons had to fall back onto the acid. So before, the acid, the A, was sharing its electron with the hydrogen. But now, since this electron fell back, we have an A with 2 electrons. Therefore, we are electron rich, so overall the charge is more negative. Okay? Now, another thing that we need to note. Whenever we have an acid-base reaction, the base always gains a hydrogen, the acid always loses it. And this causes two things to appear in our product side. So instead of having a base, we now have the conjugate acid, right? And over here, we have the conjugate base. Okay, now this can be a little bit confusing to understand because you have to remember that the conjugate acid comes from the original base, and the conjugate base comes from the original acid. Why? Well, let's think about it like this. When the base grabs the hydrogen, it is now in a position where it can lose the hydrogen. So the base turns into a type of acid. Therefore, we call it the conjugate acid of the base. Similarly, when the acid loses its hydrogen to the base, it becomes electron rich. Therefore, it is in the position now to grab a hydrogen and therefore becomes a conjugate base. Now, depending on certain factors within these reactions, sometimes the products will be more stable than the reactants, or sometimes it'll be vice versa, where our reactants are not very stable and the reaction is actually going to want to go back towards the reactants. We're going to discuss how we know when this occurs later. Okay. So what is a strong acid or base? You're going to hear this term a lot, and it's super, super important that you understand what it means. So a strong acid isn't necessarily that it's going to be super corrosive. Normally it is, but that's not the true technical definition. A strong acid or base is a compound which dissociates 100% in solution. And dissociates, in case you don't know what that means dissolves. So it's important that we kind of review what it means when something dissolves. So I'm going to give us a really basic acid. Let's do hydrochloric, HCl. Now, there is a list of strong acids and bases. If you just search them up, I would highly recommend that you know what they are. We're not going to go through them here, but I believe there are 7 strong acids and a few strong bases. It's more important that you know your strong acids. But this acid right here, hydrochloric acid, is strong. So what that means is if we put it in some water, what's going to occur is that in the water, in the solution, we are going to have separated H plus and Cl minus ions. It's going to dissociate 100%. Now, an example of a weak acid is hydrofluoric acid. Hydrofluoric acid is actually very dangerous, but it's not a strong acid, so it's not going to dissociate. Instead, we're going to have in solution some separated H plus and F minus, but the majority of it is actually going to stay together as a solid, right? So at the bottom of our little beaker, you will see that the acid will kind of stay together in clumps. Now, this is if we have a solid in the first place. If the hydrofluoric acid is already liquid, then it will stay liquid, but it will not mix in and dissolve with the water. Super important to recognize the differences because it changes what occurs with our reaction. Okay, now let's give one last example with a strong base. A super common strong base is NaOH, sodium hydroxide. Now when we put this in solution, the same thing's going to happen, except, oops, let's make our water blue, of just getting 2 ions, we're going to get an Na plus, and then this might confuse some people, we're going to get an OH minus. So here we have an elemental ion, meaning that it's one element, but here we have a polyatomic ion, right? So we have 2 different elements, but overall it still has a charge of minus. So don't get confused, it's perfectly okay if this occurs just so long as it completely dissolves into 2 parts. Alright, PKA. What is PKA exactly? So this confuses a lot of students, but if you think back to your introductory chem class, think about the titration. So the pKa is the pH at which the moles of acid equal the moles of base. So if you'll remember that when we're doing titrations, right, the whole point is that we have some solution with an unknown concentration and we want to figure out what it is. We do this by adding either an acid to a base or a base to the acid, depending on what we're starting out with. So let's say we have NaOH in solution and we don't know the concentration. So we're going to add some amount of HCl. Okay, and this is going to react out to form neutral water eventually. Now, at the pKa, we're going to have in solution, we're going to have equal amounts of H plus Cl minus, and we're going to have equal amounts of Na plus OH minus, and then OH minus, right? So for every hydrogen, there's also a sodium, and for every chlorine, there's also a hydroxyl group. So basically what this is saying is that the amounts of the acid equal the moles of the base. This is important. Now remember that the pK is technically the pH, but it's not the exact same, right? So it does act like pH, but normally pH goes from about 0 to 14. pKa can go into the negatives, and it also can go well above 14. But it acts the same way in that the lower the pKa, the stronger the acid. And the higher the pKa, the weaker the acid and the stronger the base. Okay? Super, super important that you guys remember this. Okay? Because this is going to help us determine what type of reaction occurs and how fast. Okay, so next we have our PKA table. This is a pretty long table. We're not going to go through all of it. We're just going to kind of go through the major compounds that I think it's really important for you guys to know. Now, probably for your organic chemistry class, you are going to have to memorize all of these. These are functional groups, and so these are important because they can help us to determine variance of a compound and what its pKa is most likely going to be. So I highly recommend that you memorize this at some point. All right, let's go through. So here I've given the compound name, then what its structure looks like, and its pKa. Remember, the lower the pKa, the more acidic. So our most acidic thing on this list is hydroiodic acid. We're going to go through and just list a couple. So our hydronium ion, you will see this a lot, and I mean a lot, in your organic chemistry class. Its pKa is going to be around -4, so still pretty acidic. Keep going. Carboxylic acid, this is going to be a big deal in organic chemistry too, so make sure you know it. It's going to be between 4 and 5. Okay, then we have our ammonium. This one's important because it is a plus charged ion, so it's definitely going to be more acidic than its original basic counterparts. So its pKa is going to be 10. Next, we have the ever famous H2O, or water, and this one also very important to note. It's going to be 14. Now, one thing I want you to note, that water is the conjugate base of the hydronium ion. In the hydronium ion, we have, we have 3 hydrogens, 1 oxygen. And since that's 1 more hydrogen than our water, which is H2O, the hydronium ion is going to be more acidic. Okay. Alcohol, also very important. It's going to be between 15 and 17. An aldehyde, notice aldehydes and ketones are from the same kind of family, but it's different in that an aldehyde has a hydrogen attached to this carboxyl group, whereas a ketone has another R group. And anytime you see R, it really just means a carbon group, any carbon group you can think of. So the aldehyde, its pK is going to be 17, the ketone is going to be 20. So notice that the ketone is more basic, and we're going to go through why in a second. The nitrile is going to be 25. You'll notice that a lot of things around here are going to be 25. The alkyne, also 25. An alkyne is any carbon group or chain that has a triple bond involved. Okay, then an amine, it's going to have 35 as its pKa. An alkene, it's in the same family as the alkyne, except instead of a triple bond in the carbon group, will be a double bond. So it'll be 44. And finally, alkane, it's going to be a carbon group with all single bonds. It's going to be 50. This is going to be our most basic thing. Another thing I want to point out in this is that all of the acidic hydrogens, meaning the ones that we're looking at in order to protonate the solution, the ones that we're going to be giving away, this is going to be colored in red. Okay, and lastly, I want to talk about our alkyne, alkene, alkane. Super important and an easy trick to remember this. It goes in alphabetical order. So the A comes first in the alphabet, and it's single bonds. The E comes after the A, and has double bonds. And then a Y comes way after in the alphabet, and it's a triple bond, right? Okay, let's keep going. Okay, so now we're going to explain why certain things are more acidic than others. Okay, and it's based on these things called electron withdrawing and donating groups. But in order to understand these, we need to know what the inductive effect is. So basically what this says is that through chemical bonds, electrons can be distributed unevenly in order to create a dipole. Okay, so remember that a dipole is something where one end is more negatively charged and one end is more positively charged, right? Okay, so what is an electron withdrawing group? It's a group of atoms which are highly electronegative. Remember what this means. Electronegative atoms, they increase to the right of the periodic table and up, right? Electronegativity are atoms that want to pull electrons towards themselves. And so we see here electron withdrawing groups are groups that draw electrons towards themselves away from the center carbon chains. Because remember, in organic chemistry, it's all about carbons. And then electron donating groups are groups of atoms which are not electronegative, so they are not strong enough to be able to pull electrons toward themselves and instead push electrons away and donate them to other atoms. Now, what's important about these two groups? Okay, so we're going to see here in this first example, we have a carbon chain with a chlorine. So we know based on the periodic table that chlorine is going to draw electrons towards itself, right? So chlorine overall is going to be more negative. Okay, so these electron withdrawing groups help stabilize conjugate bases, and they destabilize, conjugate acids, and they destabilize conjugate bases. And let's look at why. So let's say somewhere in this carbon chain we have an acidic hydrogen and it gets taken away, right? So the electrons again fall back onto this carbon. So now we have a carbon that has excess electrons, so it's going to have a negative charge, right? Now remember that through the inductive effect, chlorine is constantly pulling the electrons toward itself, right? So it's actually helping to distribute this excess of electrons so that when it's pulled, this carbon isn't quite so burdened with all these electrons, right? It's kind of being distributed equally. So the charge in itself is more equally. Now, definitely, this compound is less stable than the original one, right? Where there were no ions. However, in comparison to, say, this, where there is no electron withdrawing group, this one is still more stable. Okay? Now, how would it destabilize a conjugate base? Is, let's remember with the conjugate base, a hydrogen would be added, and so we would have a loss of electrons, right? We'd be electron deficient, so overall the charge is positive. So this chlorine, it's still going to be pulling these electrons no matter what. But we're already deficient in electrons. So this chlorine is pulling from an area that already has very little to begin with. So if we keep pulling from a deficient area, this charge, this positive charge, is going to grow. Okay, and so in order to become more stable, we want our charges to be as small as possible. But when the chlorine keeps pulling, this charge becomes bigger because this carbon becomes even more electron deficient, right? So there's hardly any electrons, and chlorine's going to take them all. Okay, now electron donating groups help stabilize conjugate bases and destabilize conjugate acids. Now, why is this? So let's look over here at this atom that I've drawn, and let's imagine that we lose a hydrogen here, right? So we're acting like this hydrogen is now acidic, so we're going to get this new molecule where this carbon, because it's lost a hydrogen, is now negative because it's electron rich. Remember, because these electrons will fall back, right? So it's electron rich, so it overall has a more negative charge. Okay, and so anytime we see donating groups, it's usually going to be a hydrocarbon group, meaning there's going to be carbons connected to hydrogens, right? So over here we have another methyl group. Okay, so this is going to act as a donating group, right? So it's going to be overall donating. So this is actually going to destabilize this because already this negative charge is electron rich, right? So it already has an abnormally large amount of electrons. So we don't want to be donating more because what is this going to do? It's going to increase that charge. And in order to become more stable, we want the charges to be as small or as neutral as possible. Now let's imagine the same scenario, but if we were to instead add a hydrogen to this carbon. So now, because we've added, we are electron deficient because now that carbon has to share with one extra atom. So it's going to be a positive charge. Well, now we still have this donating group, and so this area is electron deficient. Well, now we're donating some electrons. So now we're making this charge smaller because we're giving it a few extra electrons. Okay, and so that's how these electron withdrawing and donating groups help to stabilize different types of acids. This is super important to remember. Alright, next, and finally, we're going to talk about estimating pKa. So the first thing we do is use the table to see if there's an exact value. If there is, that's what your pKa is. If not, we're going to keep going. We're going to estimate based on its closest functional group. So we're going to see, okay, well, what functional group does this look like? And then we're going to use the periodic trends, such as with the electron withdrawing and donating group, to compare the stability. Okay, so I have two examples here. The first one, we're looking for the most acidic. We're going to rank them in order. The second one is going to be the most basic. acidic, basic. So remember, acidic, we want the lowest number, and basic, we want the highest. Okay? So let's start with our acidic groups. Okay? Well, we see, first of all, that we have right here a carboxylic acid. Well, we know what its pKa is going to be, right? It's going to be 4 to 5. Okay? So we just did this by looking at the table and we had an exact match. Okay, here we have a carboxylic, right? This looks exactly the same, except we have a chlorine. Okay, I want you guys, we're not going to answer what its pKa is yet, but start thinking about what that would do to its pKa. Okay, next we have an alkene. You see we have this double bond. And we have a hydrogen, oh, my bad, that positive charge isn't supposed to be there, but we have an alkene. Looking at our table, we automatically know what its pKa is going to be, 44. Nice. And finally, we have an ammonium. Okay, so we know what this one's going to be. It's going to be 10, right? And this was just based off our table. But there is one that's not quite on our table. It's this guy right here. But let's look at what we do know. We know that part of its structure is a carboxylic acid. So we know that already the pKa has to be somewhere close to 4 to 5. But what is attached to it? This chlorine group, right? And we just discussed this, but is chlorine withdrawing or donating? It's going to be withdrawing. So let's imagine, because we're testing acidity, what would happen if we got rid of this hydrogen? Okay, let's redraw the structure. We'd have chlorine, this guy. So remember, when we attack this hydrogen, the electrons are going to fall back, so oxygen is going to have a negative charge. Now, this is the conjugate base, right? So it has a negative charge. Will withdrawing groups help stabilize or destabilize this? Well, since it has a negative charge, it's going to help stabilize, right? Because we're electron rich. So we need to decrease this charge by getting rid of some of those electrons. So in fact, chlorine is going to stabilize. Now, remember, when we are stabilizing something, our energy is going to be lower. So anything that has a more stable conjugate base or acid is going, since we're looking at acidity, anything that has a more stable conjugate base is going to be lower in pKa. So we're not going to give this one an exact value, but we're going to say that it's less than 4 to 5. And I want to make this apparent that a more stable conjugate base has a lower pKa. Okay, so now we're going to rank these. Well, we can see that we're going to be, here's first. Remember, we're ranking acidity, second, third, fourth. Perfect. All right, now let's move on to the next one with our basicity. So we're looking at basicity, so we're looking at the highest pKa. Now, mind you, we could be looking at pKb. pKb is the same thing as pKa, except we're dealing with bases. So if you're looking at pKb, remind yourself that the lower the pKb, the stronger the acid. But we're still just looking at pKa, and that's what you're mainly going to be looking at in organic chemistry. Okay, so one thing I want you guys to note is all of these structures have this benzene ring, right? This is what we call this. So since all of them have it, it's going to affect them in the same way. So we're going to kind of ignore it, but we don't want to ignore it completely. So one thing I want you guys to note is that a benzene ring helps to distribute charge. Helps distribute the minus charge. Okay. So another thing I want you to notice is that 3 out of the 4 ions here are actually conjugate bases, right? The only one that's not is this guy over here. So this one is just an alcohol. Okay, so we're going to look at our alcohol and see that, well, we know what this guy's pK is based on the alcohol, right? It's going to be around, let me just see, 15 to 17, right? So its pKa is 15 to 17, right? Because this is just an alcohol based on that guy right there. But let's go ahead and imagine, remember, we're talking about basicity, okay? So imagine if we added a hydrogen, what would we get? Well, we'd get a benzene ring. This is another way to draw a benzene ring with OH2 plus. Now, the benzene ring does not help distribute positive charge. This is actually going to be a lot less stable than a lot of these other rings, right? Because since it's stable where it is now as an alcohol, it's really not going to want to add a hydrogen. And remember, the stronger the base, the more it really wants to grab a hydrogen. But this guy is already stable on its own, so it really doesn't want to add a second hydrogen, because then it actually becomes less stable. Okay, so now, remember, we're dealing with bases, so we're going to go through and imagine all the conjugate acids by adding a hydrogen. Okay, so let's start with the first guy on the left, and imagine if we added the hydrogen. Well, we'd get something that looks like this. OH. Well, we just saw that this guy is really stable and has a charge of 15 to 17. So, if we have a stable conjugate acid, that means the original base is strong. Okay, so again, a stable conjugate acid means a stronger base. Okay, so overall, we are going to say that this guy's pKa is going to be greater than 15 to 17, right? Because we're looking at bases. All right, we're going to do the same thing here. You would get NH2. Okay, so we know what this guy's acidity is, or sorry, it's pKa. Oh, I don't have this one written down. Let's go and look on our table. Looking for NH2. Oops. So we can see that we have NH4 is 10, and then our NH3 is 35. So we know it's going to be somewhere in between there. I believe, I don't have this one written down, but I believe it's somewhere around 20 if I remember. Around 20. Okay? And then finally, we're going to look at this guy. We have CH3. Well, we know what this one is, right? It's a methyl group, so it's an alkane, and we know its pKa is 50. Right off the bat, because we've memorized our chart and we're good students. So now we're just going to rank these. Okay, well, we see this one's the highest, so it's going to be 1, 2, 3, 4. Beautiful. And the last thing we're going to go through is how to write acid-base reactions. So first, write the complete reaction, then identify the acid and the conjugate base, compare the pKa values, and finally, the most important thing I want you guys to know is draw the arrow towards the larger pKa, or the weaker acid. Okay, it always goes this direction. So let's look and see if we can figure out what our acid is. We know this is a strong acid, and this must be the base then. Okay, so that means that this is the conjugate base, and this is the conjugate acid. Right? Perfect. So now we need to look at our pKa's. Okay, well, we know what HCl is. We wrote it down on our table. HCl is going to be -6. Okay, now we're going to look at the pKa for our conjugate base, NH4, which we know is 10, right? So where is the larger pKa? It's this buddy right here, right? So we're going to draw our arrow. When I'm talking about arrow, I'm talking about this one, right? Because remember that with the acid base, we can either go towards our product, towards our reactants, and it's going to go in whichever direction we have the higher pKa. So overall, our reaction is going this way, right? If somehow this had been reversed and the NH4 had been on the reactant side, then the arrow would be going the opposite direction. Okay, so I hope this made a lot more sense. Again, feel free to download those notes and leave any questions you have in the comments below. I wish you guys good luck, and I'll see you in the next video. Bye.